So we have here chapter 6.2, the iteration method. The iterative method is well suited for calculation by any digital computer. Let us assume a two-dimensional problem in which the potential does not vary with the z-coordinate and divide the interior of a cross-section of the region where the potential is desired into squares of length h on a side. A portion of this region is shown in the figure. The unknown values of the potential at 5 adjacent points are indicated as VO, V1, V2, V3, and V4. This figure shows a portion of a region containing a two-dimensional potential field divided into squares of side h. The potential VO is approximately equal to the average of the potentials at the 4 neighboring points, which is represented by the equation VO is equal to 1/4 V1 plus V2 plus V3 plus V4. The iterative method merely uses this equation to determine the potential at the corner of every square subdivision in turn, and then the process is repeated over the entire region as many times as is necessary until the values no longer change. The method is best shown in details by an example. So for simplicity, let us consider a square region with conducting boundaries shown in this figure. The potential of the top is 100 volts, and that of the side and the bottom is 0. The problem is two-dimensional, and the sketch is a cross-section of the physical configuration. The region is divided first into 16 squares, and some estimate of the potential must now be made at every corner before applying the iterative method. The better the estimate, the shorter the solution. First, we find the value of both gap 1 and gap 2. So, in order to find the value of gap 1, we should consider the potential at the top, which is 100, and that of the side, which is 0, then divide it by 2. Then we will have 50. Since gap 1 and gap 2 is in symmetry, we have the value of gap 2 as 50 as well. So, to determine the value of VO, we shall use the formula VO is equal to 1/4 V1 plus V2 plus V3 plus V4. We have the value of V1 as 100, both V2 and V3 as 0, as well as V4. So we have VO as 25. In order to find the value of VA, which is at this point, let us consider this point VA. We will use the formula that we had for computing VO. So VA would be equal to the surrounding potentials, which are 0. We have the computed value of VO, which is 25. Then the potential at the top, which is 100. And of course, the value of gap 1, which is 50. We will have the value of VA as 100 plus 50 plus 25 plus 0 over 4, which is equal to 43.8. We have VA as 43.8. Since VA is in symmetry with this point, we will consider this point as 43.8 as well. So, let us now compute the value of VB at this point. Let us consider this point VB. In order to compute the value of VB, we shall use the value of VA, VO, this value, and 100 volts. As you can notice, we are using the potential that surrounds the value that we are finding. So we have VB as 25 plus 43.8 plus 100 plus 43.8 again, and then divided it all by 4. We have the value of BB, which is equal to 53.2. We have BB as 53.2. Repeating this method from the equation given before, considering the potentials surrounding the point, we can acquire the other values needed. Then we will have this point with the value 18.8, this point with the value 6.25, and looking at the figure, we will consider that this side is in symmetry with this side. Thus, this point is also 18.8 and this point is also 6.25 plus this point as 9.4. So, the initial traverse is now made to obtain a corrected set of potentials beginning in the upper left corner, working across the row to the right, and then dropping down to the second row and proceeding from left to right. So this means that we will now have our second iteration method. So to compute for the next value, we will use the first value that we had. So in order to compute for the second iteration, we have the value of VA prime, which is this point at its second iteration. We will have its surrounding points, potential points such as 18.8 plus
Kahit meaning lang ba na ito?
43.2, and the value of this gap, which is 75, plus this gap, 25, all over 4, we have VA prime as 43.0. So we then considered VA prime as 43.0. As you can see, we are using the computed value from the first iteration to compute the values of the second iteration. Repeating this method, we will arrive at the required values till we reach the last iteration, in this case, the fourth iteration. So, in the second iteration, we will arrive at values 43.0, 52.2, symmetry with this 43.0, 18.6, 24.8, 18.6, 7.0, 9.7, and lastly 7.0. So, we will reach the last iteration, which is the fourth iteration, and then arrive at a value 42.8, 52.6, 42.2, 18.7, 25.0, 18.7 as well, 7.1, 9.2, and lastly 7.1 for the last iteration. So, to consider that our value is the final or last iteration, we will consider this condition. So, we have the new value minus the old value, which is this one, in this case 42.6, over the new value, multiply it by 100%. The answer should be less than 1% to consider that what you're doing is already the last iteration. All the values presented in this table or in the table you are computing should satisfy the condition new minus old values over new value times 100%. So, if the analysis reaches the Imax, which is the maximum iteration method that can be used, and still the condition isn't satisfied, which is the previous condition of new minus old over new times 100%, then one should redo the computation. Yes, one should redo the computation from the start. Then, that's all and thank you. Hope you enjoy it.